Thank you, everyone. I'm really proud to be here. First, I will present myself. So I'm Aurélien Massiot from France. It's very hard to pronounce in English, so usually we call me Oreo, like the biscuit, in English language. So I'm a machine learning engineer and data scientist at Octo Technology, which is famous in IT in France. And this is my email address, just in case. Who has already heard about vector databases in this room? Yeah, a few people, me also. So if you know about vector databases, basically what it does, it's useful for music recommendation, semantic search, facial recognition, NLP, image search. Each time you have to compare images or videos or music, you have to use vectors. This is a representation of the information. And there is a new thing, which is RAG. Maybe you know RAG, some of you, RAG. Yeah, so if you know large language models, RAG is a retrieval augmented generation. And what it does, it's when you use a LLM, for example, ChatGPT, sometimes you want to add your organization data. So you will basically use a RAG for this. And for this RAG, you will need a vector database to put your vectors into. So today, what we are going to do is a multimodal search engine. I will show you before the repository. So this is a simple app in Streamlit. I think Streamlit is famous now. And you will see that when I enter a request in text, I will search for fashion search. So if I type, for example, NASA t-shirt, it will search for a... Sorry?
Turn off the light.
The light?
Light.
Oh, okay. Thank you. Thank you very much. So basically, if I search for a NASA t-shirt, for example, behind this, I will search for a vector similar to NASA t-shirts, which is encoded into text and image. I will show you after the process of this. For example, if I search for red skirts, it will be also a search between a vector of a red skirt and also red skirts in this database. So this is basically what I will be coding today. I will just code myself on this screen. If you want to follow on your screen, you have to go on this repository. So I will give you 10 seconds to take it if you need it. But don't worry, if you don't have the repository, I will do it myself. 3, 2, 1. Okay. So our tools today, it will be this dataset, which is from Kaggle, which is an HEM personalized fashion recommendation. And you have like 100K products in this dataset. So it's a big dataset, maybe 50 gigabytes. And I think you know embeddings. Yeah, most of you. So embeddings, it's vectors, it's the same. And this is a representation of an object. So when you encode your data, which is behind an image or a video or music, often it's an embedding, which is a vector. And it's a representation of this data. For example, this is the famous example where you have a man and a woman, which is at the same distance between the king and the queen. And in this specific Kaggle dataset, what I used for this is CLIP, which is contrastive language image pre-training. And this is a dataset trained between pairs and image text. That's why you can do a multimodal search engine with this. So for example, the image of the red dress here will be near to red dress in text. So this is something you can find on Hugging Face. So I did it for you. You've seen this application, so what I will code behind, it won't be the Streamlit interface, but I will code only the vector database behind, which will be maybe 100 lines of Python. And the application, don't worry, this is big, but really it's not that hard. You have this data set of images, so 100K images in the data set. I use Fashion Clip to transform these images into vectors. Okay. Then I will insert this data in the database that does not exist yet. And then when I type this search, white t-shirt NASA, white t-shirt with NASA logo, in fact, I translate this text into vector, and then I will search for similar vectors. Is it clear? Or I know this scheme is a bit complicated, but really it's not that complicated. You have vectors in the database, that is images transformed into vectors, a text search which is transformed into vectors, and we do the matching. Okay, so let's code. I'm just checking the time. I didn't take too much time, that's okay. So this is my repository. You see my screen, it's okay, or? Yeah. It broke. What? This is strange because I don't have the same return here. Wait a second. It's frozen. I don't know why. Wait 2 seconds, sorry. My screen is totally frozen. I don't know why. I'm so sorry for this. I won't execute code on this one, so I will just describe, because I'm afraid it will freeze again. So what we will have to do is to create a DB vector like this. Not these ones, just this one. So basically you have an ID and the vector for each of the 100K images. Then you insert the vectors. So basically that is really simple. At the vector ID, you insert an array. Okay, so 100 arrays in this specific object. I will show you after the slides, but that's the first step is to insert all the vectors. If you want to query them, you have to compute the distance between a vector and all the vectors in the database. So you have a specific distance, which is cosine similarity. Maybe some of you know it because you have this in NLP. And in cosine similarity, you compute the distance between a vector. For example, it could be a NASA t-shirt, which will be a vector. And you compute the similarity between this vector and all the vectors in the database. Okay? And you retrieve, finally, the top k vectors. For example, here I compute the cosine similarity between one vector and all the 100K vectors in the database. I sort the vectors, the distances, and I keep the top 1 or top k, top 20, for example, vectors. In this one, it's top 20 vectors. So that is not really complicated. So cosine similarity is defined as a distance between two vectors, vector A and B. You have the dot product divided by the dot, algebra, etc. Between vector A and B, the norm. Yeah. So this is a very simple distance and very simple algorithm to query all the vectors. Is it for you a good approach to do this or not? Why?
Because each time you have to calculate every time you query.
Yeah, exactly. So each time you do a query, you have to compute 100K distances and order them, and it's very costly. What is the advantage of this? There is an advantage for this.
Because you're going,
What?
because you're going through every single one of them, you're sure to return the best matches.
Yeah, exactly. So as you compute all the distances, it's exhaustive. So this is also called the exhaustive search or brute search. This is basically the distance between all of the vectors. So exhaustive search, brute force search. There is a name for this also, a term name, which is KNN, K nearest neighbors. Okay, so you compute the distance between all of this. There is a smarter algorithm which is inverted index. Who knows inverted index? Oh, thank you. So inverted index, it will be more smart. It will be smarter because you will use clustering. So if you want to improve the speed, you will do some clustering. And basically what you will do, you have, for example, 4 clusters that you can see here. You will compute a k-means, which everybody in this room knows. And you will assign a vector to the closest centroid, to the closest cluster. Okay, here, this one. So you compute the k-means. You have maybe 4 or 5 centroids, and you assign them to the the vectors to the closest cluster. For example, here you have k3, and all the search will be all the vectors will be assigned to 1. And what is the advantage of doing this? Yeah, I missed a step. And then maybe you have 10 clusters, and we'll search into 3 clusters, for example. What you will do is you will compute the distance between a point and only the centroids. Okay, so instead of comparing one vector to 100k images, you will compare just one vector to maybe 10 centroids. And then you will find into these centroids. Clear? So it's smart. Is it good? Is it a good approach?
It's better.
Yeah, it's better, it's really faster. What would be the limitations for this? So you have two parameters. You have the number of clusters, you have the number of clusters in which you search, which will be what you call n-probes. So what are the limitations?
Limitations, number of clusters, because we brute force in all the vectors inside cluster.
Yeah, so this is a limitation because at first you have to compute the clusters, it could take time, but also if you don't search in every clusters, let's admit we have 10 clusters and you search into 5 clusters, you won't have all the truth in this. So that's why you have a dilemma in this, and you have a metric which is recall. Because if you compute the exact distances with the KNN, the brute force, maybe you will have the 10 closest, the 10 closest vectors. But maybe you will miss some with the clustering, okay? So, yeah, so you have the probes here. I will show you the code for this, so I won't use PyCharm anymore on this one. Very tricky. So, we still have our cosine similarity. Of course, you will have to compute the distances, but this time you will have to init k-mean index. Okay? So as I said before, you create a k-means, which is from scikit-learn. Yeah.
Nothing on the screen.
It's okay. I will switch one last time after. You have the k-means from scikit-learn, which is very standard, and then you fit on all your vectors the k-means. And then you have some cluster centers. So, for example, you define 10 clusters. You will have 10 clusters, and after that, you just predict for each vector in which cluster it will be. Simple. So you have 10 clusters, you have 100k vectors, and each vector will be assigned to one cluster. So what you have in the end is for each cluster ID the list of vectors which will be in it. For example, you have in cluster 1 you have number 3, 45, etc. So for each cluster you have the list of vectors ID that will be in here. And then, so you have your index, which is this one. If you query on this specific index, so query with k-means, what you will do is to compute this time the cosine similarity between one query vector and the centroids only. So if you have 10 centroids, you will compute between 1 and 10 vectors. Very simple. So it saves a lot of time. You sort all the distances, and then you filter a certain number of clusters. For example, if you had 10 clusters, now if you take n probes equal to 5, you search in the 5 closest centroids. And in these 5 closest centroids, you really compute the distance between all the vectors in these n probes clusters. Is it clear or not? This one? Maybe it's a little hard. I don't know. Okay, so very simple. I will just switch one last time, and I hope it won't fail. So again, you create one cluster, one k-means with a number of clusters. So for example, 10 clusters. You compute all the distances between one query vector and all the centroids of these clusters, and you search in only a number of centroids the closest vectors. Okay? Is it better, this one? Is this faster, or? I guess yes. Yeah. So the advantages, it's faster. It's faster. Only this one. What are the disadvantages now? As I said, you lose some precision, some recall. In fact, there is a second disadvantage. If you add a new vector in the database, you have to compute all the centroids again. So it could be a little bit tricky. We'll try to launch PyCharm maybe one last time to execute my demo. The finger crossed. And this one. So I will show you on this specific demo that it's really faster when you use this k-mean. So make run. It will take some time. So yeah, 100k lines of code, and you have like KNN search, which is exhaustive, and also a basic ANN, which is approximate. ANN stands for approximate nearest neighbors, and it's really fast like this. So if it launches, you will have the choice between the two algorithms to search for a vector. Maybe a little bit more time. Any questions so far, or no? Everything is clear. Okay.
Is there a better algorithm like that combines both options?
Yeah. So I will show you. I won't code these ones, but really you have better algorithms that are really faster than these ones. So for example, while it's charging, I will just give you the takeaways. and after I will show the demo. It's really easy now to create a multimodal search engine because you have these models like Clip that I showed before. And also coding a vector database is very easy. Of course, don't use this one into production, but really that's not that hard. You have also in all of the vector databases on the shelf, you have also all the algorithms for index. So IVF, this is the one that we coded here, which is very simple with the k-means. But also LSH and NOI, they are very strong algorithm, maybe more complicated, of course. HNSW also is maybe the best one today, which is very, very fast. I will show you on the demo after. And also, as I said before, you have a trade-off, a dilemma between precision and performance. If you want performance, if it's really fast, you will lose some precision, so some recall, in fact. IVF, for example, is very performance, but you lose some precision. If you search for precision, you take some ANN, k-inverse numbers. You have also this benchmark on annbenchmarks.com, if you want. This is launched. So, for example, I will type ugly dress, and you will search for ugly dresses. I hope you don't wear this today. So I don't know if you know Balenciaga, which is a French. Yeah. I'm not proud of this. So Balenciaga, you have some stuff like this, which is really ugly, and it works very well. And you see on this one, on this specific request, because I use the KINN in this specific request, the recall that is here is 100%. It's exhaustive. You search into the totality of the database. So it's, of course, 100% recall. But also, it takes time. You have 1 second, which is okay, but trust me, you will find some faster solutions. So for example, I execute the same request, Balenciaga, in 10 clusters, and I will search into 3 probes. So I have 10 clusters. My data is divided into 10, and I search for my query vector into only 3 clusters that are the closest centroids. And in this specific request, you see that it's faster. I take only 0.26 seconds, but I lose some recall. If I increase the number of probes, it will be a higher recall, but the time of request will increase also. So it's doing it. So you see that it's a dilemma, and it's really tricky to know the exact number of cluster or probes that you will have to define. So here, yeah, in this one you have 5 probes, so you search for in 5 clusters, and this one you have 90% recall, but also 45 in a request, so it increases time. It works also if I drop an image, which is very convenient. So for example, if I put this image, robe verte, which is green skirt or green dress, I don't know. If I drop an image like this, I will have the most similar ones in this database. So it's really powerful because you see you can search in this multimodal way. You can search for an image to an image, or also a text for an image. And this is really easy. As I said, it's like 500 lines of code for this. My final demo will be, for example, HNSW, which is a very hard algorithm to code. There are a lot of papers for this, but you have a library for this that is called, wait for this, run. HNSW, you have a library which is called HNSW lib that you can embed into your vector database. And this is a very powerful one. Of course, I will not code it because it's really, really hard, but you will see that it's really, really faster. And all your algorithms in the current engines, for example, pgvector, chroma, annoy, all these vectors databases, they use HNSW because it's really, really fast and you don't lose some recall. It's, I mean, it's okay. So it will take time to launch, but it's really easy. So if you go to Amazon.com or you go to HEM, what you have behind it's a vector database like this, but a serious one, not this one, of course. So maybe a little bit more time. So yeah, KNN it will be using exhaustive search and in approximate nearest neighbors, which has approximate algorithms. You can have HNSW, you can have annoy, and you can have this one, for example. So same, I will search for a NASA t-shirt, and this one is using HNSW. And you will see in this benchmark, HNSW, yeah, you see 90% of recall, but only, yeah, 0.0000 seconds. And it's really, really, really faster. If you search for, I don't know, a red skirt, for example, it takes only a fraction of seconds, yeah, to return this, which is pretty convenient. I mean, it's fine, and it's really a magnitude faster. All right. So this was my bonus. If you want to stay in touch, you have my my QR code here. I'll go back to France today, but if you go to the Olympic Games, maybe we stay in touch. You have also the GitHub here if you want to play, and you have also an article which is in French, but if you translate it, I mean it's okay. I'm really, really sorry for all the stuff that that didn't work, but I'm really proud to be here. And thank you very much.